13.23. In a periodic table, the average atomic mass of the magnesium is given as 24.312 U. The average value is based on their relative natural abundance on Earth. The three isotopes and their masses are 12 Mg24, its mass 23.98504 U, 12 Mg25, mass is 24.98584 U, and 12 Mg24, 25.98259 U. The natural abundance of 12 Mg24 is 78.99% by mass. Then calculate the abundances of other two isotopes. Now average atomic mass of Mg, that is given to you. Then after mass of each isotope, that is also given to you. And abundance of one isotope 12 Mg24, that is 78.99%, that is given to you. It implies that, say, total we take 100%, out of which 78.99, that is 12 Mg24. So 100 minus 78.99, that is 21.01%, that is the rest abundance of other two isotopes. So now we can write 24.312, that is equal to, for 12 Mg24, the mass, that is 23.98504, and it is 78.99%. So into 78.99. Then after, suppose 12 Mg25, whose mass is 24.98584, that is X percentage. Then we can write plus 25.98259, 12 Mg26, that will be 21.01 minus X. કારણ કે બાકીના બે જે છે એ 21.01% માં છે, એમાંથી એકને આપણે X લીધો, તો second one, that is with abundance of 21.01 minus X. The whole thing divided by 100. Now solve this equation, you will get X. Okay, 12 Mg25 નું abundance મળી જાય. Then calculate 21.01 minus X, you will get the abundance of 12 Mg26. Clear to all of you? 13.24. The neutron separation energy is defined as the energy required to remove a neutron from the nucleus. Obtain the neutron separation energies of nuclei 20 Ca41 and 13 Al27 from the following data. Now, atomic mass for Ca, atomic mass for Al, then atomic mass for 20 Ca41 and atomic mass of 13 aluminum 27, all are given to you. Okay. Now, first of all, list out all these atomic masses and mass of neutron. Now for 20 Ca41, so prepare the reaction. 20 Ca41, so one neutron is released. It implies that now here 20 Ca40, Z remains same one, plus one neutron. So neutron separation energy, simple thing, mass defect into C square. So now delta M into C square, that is mass of 20 Ca41 minus mass of 20 Ca40 minus mass of neutron into C square. Substitute the value of all these masses which are given to you in terms of U. So to calculate energy, directly multiply it with 931.5 and you will get energy in terms of MeV. Then after, for 13Al27. First prepare the reaction. So 13Al27 neutron is released, will get daughter nuclei, that is 13Al26. So again we can write the neutron separation energy delta m into c square, delta m the mass defect. So left hand side mass, that is mass of 13Al27 minus mass of 13Al26 minus mass of neutron into c square. But all the masses given to you are in terms of u. Therefore, directly multiply this mass with 931.5. Your answer will be in MEV. Clear?
Yes, sir.
13.25. A source contains 2 phosphorus radionuclides, 15p33, half-life that is 14.3 days, and 15p33, half-life that is 25.3 days. Initially, 10% of the decay, that is from 15p33. And now how long? One must wait until 90% do so. Okay, 132 લઈ લેજો આમાં. So 15p32, this first one. અહીંયા printing mistake છે. So half life that is 14.3 days. 15p33, half life capital T dash, that is 25.3 days. Okay. Now initially 10% decay that came from 15p33. So we can write now, initially 90% of the mixture is p32 and 10% of the mixture is p33. Okay. Now suppose at time t 10% is of p32 and 90% is of p33. After time t this happens. Okay. Now let x equal to total undecayed mass initially, and then after y, that is total undecayed mass finally. So initially number of p32. તો જુઓ ઇનિશિયલી અહીંયા આપણે મિક્સચરમાં p32 નું એબન્ડન્સ 90% છે. તો 0.9 into x, that is the initial number of p32, and number of p33. So initially p33, that is only 10%. So total mixture nu 0.1 into x, a number of p33 hoy. Then finally number of p32, that becomes 10%. So 0.1y, and p33 that becomes 90%. So number of p33, that is 0.9y. Now for p32 and p33 we can use the equation n upon n0, that is equal to half into t upon capital T. Similarly for 33 also n upon n0 equal to half into t upon t dash. Now for 32 n, that is final 0.1y upon 0.9x initial, that is equal to half into t upon capital T. Similarly here for 33 final, that is 0.9y, initial that is 0.1x, that is equal to half into t upon t dash. So now here take the ratio of these two. This one is 1/9 y by x, that is this one, and this is 9/1 y by x equal to 1/2 t dash. So 1 upon 81, that is half raised to t upon capital T minus t upon t dash. So Resultantly, we get 1 upon 81, that is half raised to T upon capital T minus T upon capital T dash. Now take log on both the side, and then after take small t common, substitute the value of capital T and capital T dash, and then solve this equation. You will get the time after which this happens. Clear to all of you? 13.26. Under certain circumstances, a nucleus can decay by emitting alpha particle more massive, a particle more massive than an alpha particle. Consider the following decay processes. 98 Ra 223 gives you 82 Pb 209 6C14, and 88 Ra 223 gives you 86 Rn 219 plus 2He4. Calculate the Q values for these decays and determine that both are energetically allowed. Now 88, 98 હશે અહીંયા આગળ ને 82 ને 688 ના અહીંયા 88 હશે તો ઓકે 88 Ra 223 gives you 82 Pb 209 plus 6C14. Now mass of 88 Ra 223 that is given to you. આગળ એક એક્ઝામ્પલ માં આપ્યું હતું, એ આપણે ડાયરેક્ટ લીધું છે. આ એક્ઝામ્પલ ઇન્ડિપેન્ડન્ટ પૂછાય તો તમને આપશે એ લોકો, એની ચિંતા ના કરતા, એટલે ગોખતા નહીં. Then atomic mass of 82 Pb 209, that is this much U. Then mass of 6C14, that is this much U. Now Q value, that is left hand side mass minus right hand side mass into C square. So mass of Ra minus mass of Pb minus mass of C into C square. Okay. So here substitute the values of all these masses. Masses are in terms of U. So directly multiply it by 931.5. You will get the answer, that is 31.85 MeV, and your Q value answer, that is positive. It implies that this particular decay, that is energetically allowed. Now second one, 88 Ra 223 gives you 86 Rn 219 plus 2He4. Atomic mass of 86 Rn 219, that is given to you this much U. Again, to calculate Q value, here mass defect, that is left hand side mass, mass of Ra minus right hand side mass, mass of Rn minus mass of He into C square. Substitute the values of all the masses given to you in terms of U, and then after multiply it by 931.5. You will get the answer, and this answer 5.98 MeV, that is positive. So again we can say, when Q value is positive, this decay is energetically allowed. Clear to all of you? 13.27. Consider the fission of 92U238 by fast neutrons. In one fission event, no neutrons are emitted, and the final end products after the beta decay of the primary fragments are 58 C140 and 44 Ru99. Calculate Q of this fission process. The relevant atomic and particle masses are given to you. So here atomic masses are given to you for these elements. Now first of all list out the mass of 92U238, this much U. Then atomic mass of 58 Ce140, this much U. And mass of 44 Ru99, this much U. Okay. So prepare the reaction. 92U238 is bombarded by neutron. Then we get 58 Ce140 plus 44 Ru99. So here to calculate the Q value again, we have to calculate the mass defect. It implies that left hand side mass, that is mass of U plus mass of neutron, minus right hand side mass, that is mass of Ce minus mass of Ru into C square. Substitute the values of masses for all these elements. Masses are given to you in terms of U, so directly multiply it by 931.5. Your answer that will be in terms of MeV. Clear? Next, 13.28. Consider the DT reaction, deuterium-tritium fusion 1H2 plus 1H3, that gives you 2He4 plus neutron. A. Calculate the energy released in MeV in this reaction from the data. Then B. Consider the radius of both deuterium and tritium to be approximately 2 Fermi. What is the kinetic energy needed to overcome the Coulomb repulsion between the two nuclei? To what temperature must the gas be heated to initiate the reaction? Hint: kinetic energy required for one fusion event, that is average thermal kinetic energy available with the interacting particles, that is equal to 3 by 2 kT. K, that is Boltzmann constant, T, that is absolute temperature. Now mass of 1H2, that is this much U, mass of 1H3, that is this much U. So reaction, that is 1H2 plus 1H3, that gives you 2He4 plus 1 neutron plus energy. So energy, the Q value of the reaction, that is left hand side mass minus right hand side mass into C square. Substitute values of all the masses, that directly multiply it by 931.5. The answer will be in terms of MeV. Now potential energy of the deuterium tritium for head-on collision, that we can write K Q1 Q2 upon R. So as per that, K E square upon the distance between those two, that is equal to the summation of the radius of both one. So R plus R, that is 2R. So if we substitute the values of K, E and R here, we will get the energy, that is 5.76 into 10 raised to minus 14 joule. Now for two nuclei, the kinetic energy, that is 3 by 2 kBT for each one. So multiply by 2. So 2 cancel, that is 3 kBT. So temperature, that is kinetic energy upon 3 kB. So now here kinetic energy we already calculated, 5.76 into 10 raised to minus 14 divided by 3, Boltzmann constant 1.38 into 10 raised to minus 23. Solve this one, you will get the answer. And you can observe tremendous large amount of temperature is required here. Clear to all of you? Next, 13.29. Obtain the maximum kinetic energy of beta particles and the radiation frequencies of gamma decays in the decay scheme shown in figure. You are given that mass of Au, that is this much U, and mass of Hg, that is this much U. Okay. Now see, mass of 79 Au 198, that is this much U, mass of 80 Hg 198, that is this much U. Okay. Now maximum kinetic energy of beta 1 minus, that is mass of Au right hand side minus mass of Hg, and here 1.088 upon 931.5 into C square. Okay, here because C given to you energy, that is in this case 1.088 MeV, that is energy possessed by beta 1 minus. So here when you are taking mass, then this energy of beta minus 1.088, when it is divided by 931.5, you will get mass of beta 1 minus into C square. So now substitute mass of AU, mass of Hg, this one as it is, and directly multiply by 931.5, you will get maximum kinetic energy of it. Then after maximum kinetic energy of beta 2 minus, this one, its energy, that is 0.412 MeV. Okay, so maximum kinetic energy of beta 2 minus, that is mass of AU, mass of Hg, mass of beta 2 minus. So that is energy, that is 0.412 upon 931.5 into C square. So substitute the mass of AU, mass of Hg, this one as it is, directly multiply by 931.5, and you will get the energy in terms of MeV. And here the frequencies of radiation emitted, that is frequency F1, that is equal to E1 upon H. હવે જો અહીંયા આગળ છે ને, three possibilities are there. Beta minus 1.088 છે અહીંયા આગળ, બરોબર? This is ground state, this is first excited, this one is second excited. Okay, so n equal to 1, 2 and 3. So beta 1 minus એ ડાયરેક્ટ 3 માંથી n equal to 1 માં, એટલે કે ગ્રાઉન્ડ સ્ટેટમાં જાય, બરોબર છે? પછી બીજી પોસિબિલિટી બીટા 1 માઇનસ એ પહેલા n equal to 3 માંથી 2 માં જાય અને પછી પાછું 2 માંથી 1 માં જાય. બીટા 2 માઇનસ માટે બી 2 માંથી 1 માં તો આ જ રેડિયેશન મળવાનું છે, કારણ કે it depends on energy differences only. So frequency F1, that is E1 by H. So first energy difference 1.088, from that to this ground state. Ground state energy here given to you, that is 0. So 1.088 minus 0, that is MeV. So into 10 raised to 6 into 1.6 into 10 raised to minus 19, this much joule, divide it by H, that is 6.6 into 10 raised to minus 34. Solve it, you will get the first frequency of gamma decay. Then second one, F2, that is E2 by H. So 0.412 MeV to the transition, that is ground. So 0.412 minus 0, this much MeV. So into 10 raised to 6 into 1.6 into 10 raised to minus 19 divided by 6.6 into 10 raised to minus 34. This much hertz for second decay of gamma. Then third frequency E3 by H. So third possible transition, that is 1.088 this is second one. So minus 0.412 MeV. So into 10 raised to 6 into 1.6 into 10 raised to minus 19 divided by 6.6 into 10 raised to minus 34. Solve it, you will get this much hertz for gamma 3 radiation. Clear? Chalo, next 13.30. Calculate and compare the energy released by A, fusion of 1 kilogram of hydrogen deep within sun, and B, the fission of 1 kilogram of U-235 in a fission reactor. Okay. Now see, we already discussed the proton-proton cycle in sun, due to which the energy released. So when one reaction is completed, 4 hydrogen atoms are fused, 1 helium is formed, and the total energy released, that is 26.7 MeV. In theory, we discussed this thing. Now, for hydrogen, if we take 1 gram, then it is 1 mole. So in 1 gram, 6.02 into 10 raised to 23 number of atoms are there. So in 1000 gram, because we want fusion of 1 kilogram hydrogen. So in 1000 gram, how many atoms are there? So number of H atoms in 1 kilogram, that is 6.02 into 10 raised to 26. Now, when 4 hydrogen atoms are fused, the energy released, that is 26.7 MeV. So when 4H atom fused, energy released 26.7 MeV. Therefore, when 6.02 into 10 raised to 26 atoms are fused, the energy released, that is how much? Simple thing. So energy for fusion, that is 6.02 into 10 raised to 26 into 26.7 by 4, this much MeV. Now we have to take fission of 1 kilogram uranium in fission reactor. So per fission for U-235, we get the energy, that is 200 MeV. In the theory of nuclear reactor, we discussed this thing. Now we want fission of 1 kilogram. So first of all, we have to calculate the number of atoms in 1 kilogram. So in 235 gram, number of atoms, that is 6.02 into 10 raised to 23. Then in 1 kilogram means in 1000 gram, how many atoms are there? So number of atoms in U-235 in 1 kilogram, that is 6.02 into 10 raised to 26. 1000 नहीं है, direct multiply करी दीदा छे, divided by 235. Now per one fission we get energy, that is 200 MeV. Therefore per this much number of fission, how much energy will be obtained? So energy during the fission of 1 kilogram U-235, that is 6.02 into 10 raised to 26 by 235 into 200 MeV. Now we have to compare these two. So take the ratio of E fusion to E fission and we'll get comparison. Clear?
Yes, sir.
13.31. Suppose India had a target of producing by 2020 200 megawatt of electric power. No, 200 नहीं है. A point काटी नाखजो, 2 lakh megawatt of electric power, 10% of which was to be obtained from nuclear power plant. Suppose we are given that on an average, the efficiency of utilization, it implies conversion of electric energy of thermal energy produced in the reactor was 25%. How much amount of fissionable uranium would our country need per year by 2020? Take the heat energy per fission of 235 U to be about 200 MeV. Now see, targeted power, that is 2 lakh megawatt. So 2 into 10 raised to 5 megawatt means targeted power, that is 2 into 10 raised to 11 joule per second. Okay. Now we want power from nuclear power plant, that is 10% of this one. So 10% of 2 into 10 raised to 11, that is 2 into 10 raised to 10 joule per second, that will be obtained from nuclear power plant. Now energy produced per fission, that is 200 MeV. And here the efficiency given to you, that is 25%. It implies that 25% of 200 MeV energy, that is converted into electrical energy. So we can write energy converted into electrical energy per fission, that is 25% of 200, that is 50 MeV. So that is 50 into 10 raised to 6 into 1.6 into 10 raised to minus 19. That is 8 into 10 raised to minus 12 joule. Now, energy for 1 year. હવે જો અહીંયા energy per second, that is 2 into 10 raised to 10 joule. તો per second તમારે 2 into 10 raised to 10 joule energy જોઈતી હોય તો એક વર્ષમાં કેટલી જોઈએ? So energy for 1 year, that is 2 into 10 raised to 10 into 3.15 into 10 raised to 7. આટલી જોઈએ. Okay. Now see, 8 into 10 raised to minus 12 joule, that is obtained per one fission. Then this one, 6.3 into 10 raised to 17 joule will be obtained from how many fissions? So number of fissions per year, because this is the energy per year, that is 6.3 into 10 raised to 17 upon 8 into 10 raised to minus 12. So your answer will be 0.7875 into 10 raised to 29. It implies that per year you have to make this much fissions. It implies that this much number of atoms are required per year. Now, if 6.02 into 10 raised to 23 atoms are required, then the required mass of uranium, that will be 235 gram. So for 0.7875 into 10 raised to 29 atoms, how much mass of uranium is required? So mass of U235 required, that is, this one is written as 7.875 into 10 raised to 28 into 235 upon 6.02 into 10 raised to 23. If you solve this one, then your answer will be 307.41 into 10 raised to 5. You can write that is 3.07 into 10 raised to 7 gram. So 3.07 into 10 raised to 4 kilogram. This much uranium is required per year. Clear?